Hello everyone, welcome to Chemistry Simplified with Rahul Coaching Academy. Today we'll be discussing the unit solutions from class 12th chemistry, and this is going to be the first lecture for this topic. Let's quickly understand that what are the topics that we'll be covering during this lecture. We'll be talking about what is a solution. We'll also talk about what are the various types of solution, and we'll also understand about the units of concentration. Now this unit is relatively easy if you already know the background of mole concept from class 11th. If you do not know that thing, do not need to worry. We'll actually cover up all these things. This is going to be kind of an introductory video to this particular unit. So let's get into this particular topic by understanding first of all that what is a solution. Now, a solution is a homogeneous mixture of two or more substances whose composition can be varied within certain limits. Now, we already know these things, right? We see this in this diagram right now that we have a solute. Now, what is a solute? We already know what is a solute, right? What is a solute? A solute is a component, which is present in a lesser quantity, right? We already know this thing. Solute is a component which is present in a lesser quantity. Similarly, we also have a solvent. Then what is a solvent? Solvent is a component which is present in larger quantity. So we have already known these concepts since class 9th. We have done this thing, right? So what is a solute? Anything which is present in a lesser quantity, and a solvent which is present in a larger quantity. Now as we see in the diagram that we are adding some solute into this particular solvent, and then we shake that particular flask and we actually get a solution. So what is a solution? A solution is a homogeneous mixture. It is a homogeneous mixture of two or more substances whose composition can be varied within certain limits. That means when we add solute and solvent together, we always get a solution. So this is what is the basic concept regarding a solution. Now, how many types of solution do we have? Before even getting into the types of solution, we'll actually talk about the types of solution on the basis of the number of components being added into that solution. So for example, if there are two components, so when I say two components, that means it can be one solute and one solvent, then this is known as a binary solution. So we already know the meaning of the word binary. What is binary? Binary means two. So if there are two components in a solution, then out of which obviously one will be solute and the other will be solvent, then that is known as a binary solution. If there are three components, in a solution, for example, if a solution is made up of three different things, let's say if you have chalk powder, we have sugar and we have water, and we mix everything together, there are three components now, then this is known as a ternary solution. This is known as a ternary solution. Similarly, if you have four components in a solution, so what should this particular solution be called? You guessed it right. It should be called as a quaternary solution. It should be known as a quaternary solution. So a solution which is made up of a solute and a solvent, if it has two components, it will be known as a binary solution. If it has three components, it will be known as a ternary solution. And if it has four components, it will be known as a quaternary solution. Just for the sake of simplicity, I would really want to tell you that we only have binary solutions in our course, where we actually going to be dealing with only two components. One is going to be a solute and other is going to be a solvent. So we all understand this thing. What is a solution? It is a homogeneous mixture of two or more substances. What are those substances called? It is either one is going to be a solute, other is going to be a solvent. Solute is basically something which is present in a lesser quantity, and solvent is something which is present in the larger quantity. We all understand that thing? Let's see what is the next topic. The next topic that we have is types of solutions. Interesting topic. So now we have three different things here. This is 1, this is 2, and this is 3. So now what we really need to understand here is that what kind of solutions are we talking about? Anything which is in this middle box here, is basically the solvent. This is the solvent. Solvent means in this first case, gas is going to be the solvent and solid or gas or liquid will act as the solute. Similarly, in this case, liquid will act as a solvent and then solid, gas and liquid obviously will act as a solute. And in this case, a solid will actually act as a solvent. And again, solid, gas and liquid will be acting as solutes. Let's talk about the first case. For example, if you have a case where I'm trying to mix solid into a gas, so it's a solid gas solution where solid will be acting as the solute right now, and that means solid will be present in the lesser quantity with respect to the gas that we are adding it in. Can you give me an example of a solution where we are adding solid in a gas and solid is acting as a solute and gas as a solvent? It's a pretty simple example. We can have dust in air, dust particles in air, for example, where air is in a very large quantity and dust particles are quite minute over there, right? So dust in air becomes an example of solid in gas solution. Similarly, what about if you have a solute as a gas and a solvent as a gas as well? That means mixture of two gases. Can you give me an example of that? Very common example, air. Air is a mixture of gases where one of the gas can be considered as the solvent and the other can be considered as a solute. Similarly, if we have, for example, liquid acting as the solute in this case and gas being the solvent, that means liquid is dissolved into gas. Can you think of an example? Again, a very common example, water vapor. Why water vapor? Because the liquid droplets will be in a lesser quantity as compared to the gas they are dissolved into in the atmosphere, and thus liquid will act as a solute and gas will act as the solvent. So we all understand the examples, right? Let's talk about the second example where liquid is basically the solvent now, and solid or gas or liquid are going to be acting as a solute. So for example, in the first case, liquid is the solvent and solid is basically the solute. These are the very common solutions that we come across in our day-to-day life where we are adding some kind of a solid into a liquid. What can example be? A salt in water, a sugar in water, right? Where we are adding a pinch of salt or some sugar into water and that gets dissolved into that solution. So that makes a salt solution, that makes a sugar solution, right? Then solid is acting as a solute and liquid is acting as a solvent. Similarly, if I talk about gas and liquid, very common examples, any gas which is dissolved into water, any gas which is dissolved into a liquid will be acting as a gas liquid solution where gas is going to be the solute and liquid, in this case water, is acting as the solvent and oxygen is acting as the solute. Similarly, we could have liquid solutions where there are two liquids which are miscible. Miscible means they can mix together and they can actually form a solution. What example can we think of? Ethanol in water, right? So ethanol is actually soluble in water where ethanol is in liquid form, water is also a liquid, and thus this particular thing is also acting as a solute solvent solution where ethanol is the solute and water is the solvent. Do we all understand these things? We can obviously take any other examples apart from these examples as well. I have picked up these examples so that you guys remember these things. These are very simple examples. Okay, let's talk about the third case where we have a solid as a solvent. Now this is a pretty unique situation where a solid is acting as a solvent. Usually solvents are associated with being liquids or gases, but solid being a solvent is a very unique case. Let's consider an example. How can we have solid into a solid and they can still make a solution? Of course, yes, they do make it. We can think of alloys. What are alloys? They are a mixture of two or more than two metals. So when two or more than two metals are actually mixed together to form another compound which is known as an alloy, that is actually acting as a solid solution. Okay. Similarly, what can we think of a gas in solid solution where gas is now acting as a solute? This is a very reverse case here where we actually had solid as the solute, which is a pretty common thing to at least understand, but solute and that to a gas into a solid, it's a very difficult situation again. Can you think of an example? Oh, example is hydrogen over palladium surface. This is actually a process which is associated with adsorption, of gas. We'll be dealing with this in surface chemistry in the later units. But this is actually an example where hydrogen gas is acting as a solute and it's getting dissolved on the surface of this particular solid, palladium. Similarly, we can think of a liquid solid solution where liquid is acting as the solute. Can you think of an example? Now the example is an amalgam. What is an amalgam, guys? What is an amalgam? Amalgam is an alloy as well, but amalgam is an alloy where we actually have one metal as mercury, right? If one of the metal in that alloy is mercury, then that particular alloy is known as an amalgam. So we pretty much know that mercury is the only metal which is going to be existing in the liquid state at room temperature. Thus, this particular amalgam, mercury, which is Hg, acts as the solute, and it is going to be mixed in any other solid or any other metal, and that will actually form a liquid solid solution. So do we all understand what are the types of solutions? So either we can have or we can just write it this way, for example, that if we have a solvent, so what solvents are possible? We can either have a gas solvent, we can either have a liquid solvent, or we can either have a solid solvent. But in that case, what are the possible solutes now? The possible solutes are, this can be either solid or liquid or gas. Similarly, again, either solid or liquid or gas, or again solid, liquid and gas, where we have different examples from these three charts. Do we all understand this thing? It's a pretty simple thing, guys. Okay, let's move on to the next thing. What do we have? We have units of concentration. Now this is what I was talking about, the mole concept. So if you are really good with this thing, the unit and the chemistry becomes really easy. If someone did not pay that great attention in 11th and they do not understand mole concept, or they do not remember the concepts, then I'm here for you guys to help you guys revise all these things. So let's understand what are the possible units of concentration and the various units of concentration we'll be using throughout this unit and the rest of our chemistry as well. The first of all, we need to understand what is a concentration. Now what is concentration? Now this term is pretty common, but what is concentration? It is the amount of solute present in the given quantity of the solution. So now whenever we have a solution, so for example, if we have a bucket and it is filled with water, let's say there is a bucket which is filled with water. Now if I add certain component A into this, let's say A is sugar, right? So I add sugar, for example, into this particular component B, and B is water right now. So do you say we are going to have a solution? Yes, we are going to have a sugar plus water will actually produce what? It will produce a sugar solution. We all know this. This is actually a solid into liquid solution, where sugar is acting as a solute and water is acting as the solvent. So we all know that thing. So now obviously if I say that it is a 1 liter water, and if I add 10 grams of sugar into it, then what is the amount of sugar or amount of solute present in that particular amount of solution, the entire solution? Then it's only 10 grams. That means it gives you the concentration of that particular sugar. So what is concentration? That how much solute have you added, what is the amount of solute that you have added in that particular solution, so that that solution has been made, right? That how much solute has been added to that given solvent to create that particular solution. Do we all understand that thing? That is what is meant by concentration. Now the second pointer says that the concentration is described either qualitatively or quantitatively. Now again, what is meant by this particular part? So let's try and understand. Qualitatively or quantitatively. What is meant by this particular part? We'll try and understand separately. First of all, what is qualitatively? Now this is something again that you guys have known for quite some time. Qualitatively, basically, what is qualitatively? Now when I say, for example, that I have a very strong acid, then what do we call that acid? We actually call it as a concentrated acid. This is what we call that acid, right? It's a very strong acid. Or what is a very weak acid? Then we actually call it as a dilute acid, right? This actually justifies what? It justifies the strength of that acid. But then what is actually meant by a concentrated acid? In this thing, acid obviously is acting as the solute. It is acting as a solute, and obviously water will be acting as the solvent. But if it is a concentrated acid, then the amount of solute will be greater as compared to the amount of solvent, or I could still say that larger amount of solute will be present in that given solvent. That will actually give you the concentrated acid, right? This is what is the qualitative analysis. Qualitative, that means we are only dealing with the quality of that particular solution. So what is the quality of the solution? That acid is in a larger quantity in that solution, which makes it concentrated. But then if I say it's a dilute acid, then acid, which is the solute, is actually present in the lesser amount as compared to the entire solution, where water again is going to be acting as what? Water will be acting as the solvent. But in this case, the strength of acid will be relatively less. Why? Because we have very less concentration of that particular acid. We already know what is concentration, right? It is the amount of solute. So if I say that there is a concentrated acid, then the concentration of acid is going to be higher. That means the amount of solute is going to be higher. Whereas if I have a dilute acid, then the concentration of acid will be lesser. That means the amount of acid in that acidic solution will be much lesser. So this is what is meant by the qualitative understanding of this particular solution. Qualitative means only on the basis of the quality of that particular solution. However, if I tell you it's a concentrated acid or it's a dilute acid, this only gives you an idea that this is going to be a strong acid or that is going to be a weak acid. But it is not telling us anything about that how much acid content is actually there in that particular solution. So rather than talking qualitatively, we prefer to talk quantitatively, that what is the quantity of that acid in that solution, or what is the amount of solute in that particular solution. So this is going to be our reference point now, that we always want to know the quantity, and that is how we actually get into the quantitative analysis. So to understand the quantity, what are the various measures, what are the various methods, or what are various units that we are going to use to find out the quantitative analysis of this particular solution. So the first thing that we commonly use is mass percentage or volume percentage. Mass percentage or volume percentage. What is mass percentage? Mass percentage is also represented by W by W, which is weight by weight, right? And has the formula of mass of solute with respect to the mass of solution into 100. Why 100? Because obviously we are trying to find out the percentage. That means if we have two components A and B, then mass percentage of A, so WA%, for example, which is mass percentage of A, will be given by what? Mass of solute. Let's say WA is a solute, and with respect to the mass of solution, what is going to be the mass of solution? The total mass of A plus mass of B, which is weight of A plus weight of B, and that will be multiplied with 100, and that will actually give you the mass percentage of A. Similarly, we can also find out the mass percentage of B in this case, which is going to be what? WB over WA plus WB into 100. So we can actually find out the mass percentage of each component, which will actually give you the very better idea that what is the concentration of that solute in that particular solvent. Similarly, in terms of liquid solutions, we can also think of, if there is one of the liquid, for example, if one of the solute is a liquid, for example, then in that case we can also think of percentage by volume or volume percentage, another method to find out the concentration. Again, for example, if I have two components A and B, and someone is asking us to find out the volume percentage, how do we find out the volume percentage of A? So let's say VA percentage will be equal to what? Volume of A. This is what the formula says, and it's quite similar to the weight percentage. Rather than weight, we are going to be using volumes. So it's going to be what? Volume of A with respect to the total volume of the solution. Total volume will be found out what? Or rather how? It's going to be VA plus VB, and that will be multiplied with 100. Similarly, we can also find out volume percentage of B. That will be equal to what? VB upon VA plus VB into 100. We all know that thing, right? Similarly, volume percentage is going to be represented by V over V. So this is usually seen in terms of liquid solutions. You might have seen a bottle, for example, it has V by V. So V by V means that this much amount of solute is present, or the volume of solute is there in terms of the total volume of the solution, and the percentage is represented in that particular form. Do we understand this particular part? For example, I'll give you an example. Example is, for example, ethylene glycol. What is ethylene glycol? Do we know ethylene glycol? Ethylene glycol, we should all know that thing. It's a pretty common example. It is a common example for what? Ethylene glycol. Ethylene glycol is an example of antifreeze. We know antifreeze, right? This has been used to put into engines in cold countries, and if we have a 35% V by V, volume by volume of ethylene glycol, then that actually starts acting as an antifreeze, right? So what is the concentration of ethylene glycol? It is having a 35% volume by volume concentration in a solution, and that is when ethylene glycol will act as an antifreeze. Just an FYI, just a good to know information. Even if you do not remember the value, it's absolutely fine. It's just a good to know information. So do we understand the first unit of concentration, which is mass percentage or volume percentage? Let's move on to the next thing then. The next thing is pretty interesting. It's parts per million. Now what is parts per million? It's abbreviated as ppm. What is parts per million? This is first of all for minute solids. When I say minute solutes, that means those solutes which are present in very minute quantity in a given solution. So for example, if you talk about dust particles with respect to the atmosphere, then they are always present in a very minute concentration. So this is first of all for minute particles. And how will we define this? This is the amount of solute. This is going to be amount of solute or amount of the component, any component that we are talking about. Amount of component. In what? In a million parts. In a million parts of solution. So rather than talking about a smaller part, we are talking about a million part. Why a million part? Because obviously the minute particle will be quite less as compared to the entire thing. So we'll talk about the million parts. This will actually give you a better representation of the concentration. How we'll check out that particular thing with an example as well. So right now, what is parts per million? It is the amount of component in a million parts of the solution, and it is actually calculated for what? It is calculated for minute solutes. Now what is the formula for parts per million? It is the mass of solute with respect to the mass of solution multiplied with a million, which is 10 lakhs, 10 to the power minus 6. Now what is meant by this particular logic? For example, we have a sample of water. Let's say we have 1 liter of water. We have 1 liter of water, and we have added, for example, we have added some chlorine into that. It's a disinfectant, right? So we add some chlorine. How much chlorine do we add? We add 3 into 10 to the power minus 3 grams of chlorine. Now if you can see this thing, it's going to be quite less. It's going to be 0.003 grams of chlorine. It's a very small amount with respect to the 1 liter volume. Now we need to understand very clearly, the mass of chlorine is in grams. However, the solution given is in liters. Now 1 liter of water is almost equal to 1 kg of water. They are quite equivalent. That means it is quite equivalent to 1000 grams of water. So this is something that you can remember for your numerical calculations as well, that 1 liter of water will almost approximately be equal to 1 kg or 1000 grams of water. Now how do we calculate ppm of chlorine? How many parts per million of chlorine can be calculated? What we're going to do, we're going to have mass of solute. What is the mass of solute? It's going to be 3 into 10 to the power minus 3 grams over what? Mass of solution, which is going to be 1000 grams, and this should be multiplied with what? This should be multiplied with 10 to the power 6. Now if you understand this thing, this entire thing will get cancelled off and we'll only be left with 3 ppm. That means there are 3 parts per million of chlorine in that particular solution. Do we understand that? There are just 3 parts of chlorine per million parts of the solution, and this is what it really helps us, because sometimes the percentage thing is quite difficult for us, because that will give you very small values of percentages as well, because again 0.003 grams of chlorine will have very small traceable percentage of chlorine into that water, so that becomes a difficult value to represent. Rather than that, 3 is a very solid value and a significant value to represent. Thus ppm is much more preferred as compared to mass percentage for minute solutes. Do we all understand that thing? This is a pretty simple concept, guys. It's not a difficult concept at all. Now let's move on to the next unit of concentration that we have, which is molarity. Now this is something that is quite common, and this is something that you guys have done earlier as well, which is molarity of the solution. Now molarity is something that was discussed in class 9th as well. We are going to quickly go to the recap and then we'll understand some concepts of that. What is molarity? It is the number of moles of solute. It is the number of moles of solute, but dissolved in what? Per liter of solution. So these are the 2 important aspects. First of all, the solute has to have the number of moles. The mass is not going to work this time. We have to calculate the number of moles, and that should always be calculated with respect to what? With respect to the liter of solution. That means the concentration or the unit of volume for that particular solution should be in liters, right? So it is the number of moles of solute with respect to the volume of solution in liters. If you do not have it in liters, we can calculate that, or we can convert that into liters by dividing by 1000. We can convert milliliters into liters by dividing by 1000. We all know that thing, right? So it is denoted by what? It is represented by uppercase M, capital M, always capital M. Do not use lowercase m, please. So in that case, what is the formula for molarity becomes? Molarity is the number of moles of solute with respect to liters of solution. When I say liters of solution, I'm talking about the volume of solution in liters. So for example, M can be written as what? It can be written as number of moles of solute, number of moles of solute with respect to what? What if the volume of solution is in ml? Volume of solution is in ml, then what we do? We just multiply it with 1000. Why 1000? Because obviously 1000 was supposed to be divided, but it gets multiplied in the numerator so that it still makes the same effect. So this can be another formula for molarity. It is the number of moles of solute with respect to volume of solution. If it is in ml, then multiply it with 1000. If it is not in ml, if it is in liters, then do not multiply it with 1000. Do we all understand this thing? This is what has been given in this key points as well, right? What are these key points telling us? The key points are saying that if you are given grams, that means if the mass of the solute is given, not the number of moles but the mass, then use the molar mass of that compound to convert them into moles. So if you are given W grams of a particular solute, then what you're going to do, we're going to divide that with the molar mass of that particular solute to convert that into the number of moles, which is N, for example, right? And similarly, if you are given ml, that means if the volume is given ml, then we have to keep in mind that there are 0.001 liters in 1 ml. This is a basic conversion. We just divide 1 ml with 1000, and that is how we can convert ml into liters. What is going to be the SI unit of molarity, guys? SI unit of molarity, it is supposed to be what? Number of moles with respect to liters of solution. It has to be moles per liter. This is what is the SI unit of molarity. It can also be represented as moles per, it can also be represented as moles per decimeter cube, right? Because 1 liter is equal to 1 decimeter cube, so we can also write it as moles per decimeter cube. So this is something that's very important. Now I'm going to discuss something here which is going to be utmost important. What does completely molarity depend upon? Molarity actually depends upon the volume of solution. Molarity is depending upon what? It is depending upon the volume of solution. Now, why am I pointing this particular point out? Volume of solution. Now, we already know that if you change the temperature of a solution, if you increase or decrease the temperature of the solution, then the volume will change as well, because the volume has the property of expansion or contraction. The liquids can either expand or contract. So if you change the temperature, then the volume will change. But if the volume changes, then this denominator changes will actually impact what? It will impact the molarity. That means molarity of the solution, it changes with what? The molar, I'll just write it down properly again. Molarity of the solution changes with temperature. Now this is a very important point, right? You got to understand this thing. The molarity of the solution changes with temperature. Why does it change with temperature? Because liquids can either contract or expand with change in temperature. That is why molarity cannot be constant at all temperatures. So if someone is asking that what will happen if you change the temperature, then the molarity of the solution will change, because the solution, that means if the liquid in that solution will have the property, or it will have the effect of contraction or expansion, right? So make sure that you remember this particular point. Do you understand this thing? What is molarity? It is the number of moles of solute with respect to the volume of solution in liters. If it is not in liters, convert that by multiplying the entire fraction by 1000. What is the SI unit of molarity? It is moles per liter, or we can also represent it as moles per decimeter cube. Do we all understand that thing? Great. What is one more thing? What is the disadvantage of molarity? That it changes with temperature due to expansion or contraction of that particular solution. We all are good with this thing? Okay. Now what do we have? We have a question based on molarity. Let's try and solve this together. What do we have? We are given 2.46 grams of sodium hydroxide. What is sodium hydroxide? What is the formula for sodium hydroxide? Sodium hydroxide is NaOH. Sodium hydroxide are dissolved in what? In water, and the solution is made to 100 centimeter cube in a volumetric flask. What do we have to calculate? We have to calculate the molarity of the solution. First of all, if you have to calculate molarity of sodium hydroxide, now as per the formula, what do we all require for this thing? We require the number of moles of sodium hydroxide. This is what we want. We also want the volume of solution in liters. We also want this in liters. If it is not in liters, we can still multiply with 1000. So we can write it as in ml and then we can multiply with 1000, and this will actually give you the molarity of sodium hydroxide. So first of all, what do we require? We require the number of moles of sodium hydroxide. Let's calculate them separately out here. We can calculate the number of moles of sodium hydroxide. So first of all, number of moles of sodium hydroxide. How do we calculate the number of moles? It is given mass upon molar mass. What is the given mass of sodium hydroxide? The given mass of sodium hydroxide is 2.46 grams. This is what has been given. And upon what is the molecular mass of sodium hydroxide? The molecular mass of sodium hydroxide is 40 grams per mole. We know how to calculate this, right? Sodium has an atomic mass of 23, oxygen has 16 and hydrogen has 1, which makes the total to 40. And this will actually give you the number of moles of sodium hydroxide. What does it come up to? When you calculate this, it will come up to 0.0615 moles, right? This is what it will come up to. We all know that we can only write mol for moles, right? So 0.0615 mole. This is going to be the number of moles present in that particular 2.46 grams of sodium hydroxide. Now what do we require? We require volume of solution in ml. Now volume of solution is given as 100 centimeter cube, but we also know that 1 centimeter cube is equal to what? What is 1 centimeter cube equal to? 1 centimeter cube is equal to 1 ml. Remember this conversion. That means 100 centimeter cube can also be written as 100 ml. So in that case, now if you have to calculate molarity, it is represented by what? Uppercase M. We just did that right now, right? So molarity will be what? Number of moles of sodium hydroxide upon volume of solution in ml into 1000. Then what is the number of moles? The number of moles are 0.0615. That will be divided by what? That will be divided by 100, which is volume of solution in ml now. This is 100 ml. And now multiplied with 1000, that is into 1000. Now what do we get after this? The molarity of this particular solution. What is going to be the molarity of the solution? The molarity of the solution is going to be 0.615 moles per liter, or we can just write it as 0.615 molar. This uppercase M will be called as molar, right? So this will actually become the molarity of the solution. Either you leave it here, this is also the correct unit, or we can just write it as uppercase M, and that will be known as 0.615 molar. Do we understand the question? It's a pretty simple question on how to find out the molarity of the solution. We all are good with this thing? Great. Let's move on to the next thing. What is the next unit of concentration that we have? It is molality of the solution. What do we have? It's a molality of the solution. Again, a very similar term to molarity, but quite different from that thing. What is molality? Molality again has to have number of moles. So it is a number of moles of solute, but this time it is dissolved per what? Per kilogram of solvent. That means in molarity we were talking about the volume of the solution, but here we are only discussing about the weight of the solvent, not the solution, guys. This is very important. This is the basic difference between molarity and molality. Molarity deals with the volume of solution, the entire solution, that means solute plus solvent, whereas molality deals with only the weight of the solvent. It does not deal with the weight of the solute. Make sure that you remember this particular part. Then it is also represented by lowercase m. Molarity was represented by capital M, uppercase M, but molality is represented by lowercase m. What will be the formula for molality? It will be number of moles of solute with respect to kg of solvent. What if the solvent is given in grams? Then we can write it as moles of solute over what? It can also be written as grams of solvent. So rather than writing the kg, we can write it in grams as well. If the question has the solvent given in grams, then we can write it in grams, and then you can multiply it with 1000 so that the entire thing gets converted into kg. Do we remember that thing? So what is molality? It is the number of moles of solute per kilogram of solvent, or number of moles of solute per gram of solvent multiplied with 1000. Then in that case, what is going to be the SI unit? What is going to be the SI unit of molality? The SI unit of molality will be moles per kg. You guessed that right. It's a pretty simple unit, right? Number of moles upon weight, so it has to be moles per kg. This is what is the SI unit of molality. Do we understand that thing? Now tell me one more thing. Just as we discussed in molarity, molarity was going to change if we had to change the temperature due to the expansion or contraction of the liquid or the solution. Do you think that molality will also change due to temperature? No, the molality does not change with temperature. So this does not change with temperature. This is a very important point again. Molality does not change with temperature. Why? Because molality depends upon the mass of that particular thing. So molality depends upon what? Molality depends upon mass of solvent. Molarity was depending upon the volume of the solution, whereas this depends upon the mass of the solvent, and we pretty much know that mass or weight will not change with temperature. It will be constant. It will not change over the range of temperatures. Thus, even if you change the temperature, if you increase or decrease it, molarity might change, but molality will not change. So advantage of molality over molarity. What is the advantage of molality over molarity? That if we can just write it as molality does not change with temperature, whereas, or rather, but molarity does. That means molality will not change with temperature, but molarity will, and that is why we have molality having an advantage over molarity. Do we all understand this thing? It's a pretty simple thing. What is molality? The number of moles of solute with respect to mass of solvent in kilograms. SI unit is moles per kg, and it has a very great value that it does not change with temperature because the mass does not change with temperature. Do we all understand this particular concept? It's a pretty simple thing, guys. Okay, if you understand this thing, let's see what do we have next. We have a question now on molality, just to make sure. Why are we doing these questions? Because we need to make sure that we are good with the concept. So we understand the concept and then we do a question with me. So try this question out with me. What you can do is that you can pause the video, try the question out yourself first of all, and then check out my solution, or you can do it with me as well. Okay, let's try and do this question. We have to calculate the molality of the solution containing 20.7 grams of potassium carbonate. What is potassium carbonate? Potassium carbonate is K2CO3, potassium carbonate. We are given mass of potassium carbonate as 20.7 grams, and it is dissolved into what? It is dissolved in 500 ml of solution. Now remember, molality will not want the volume of the solution, it will want the mass of the solvent. So we do not want that solution, we will have to change it. But for that conversion, they have also given one value. They are given the density of the solution as 1 gram per ml. What is meant by 1 gram per ml? That means 1 ml of solution has a mass of what? 1 gram. So 1 gram of solution is equal to 1 gram of solution, right? This is what is the conversion as per the density. Then if we have 500 ml of solution, we are given 500 ml of solution, then what will be the mass of 500 ml of solution? It will have a mass of 500 grams, right? So 500 ml of solution will have a mass of 500 grams. Also, what do we all require for molality? Let's write down the formula for molality first, then we'll try and put the values. What is the formula for molality? Is the number of moles of solute. So in this case, it's going to be number of moles of K2CO3, which is potassium carbonate, upon what? Upon mass of solvent in grams, because obviously we see that in grams, but if it is in grams, we'll have to multiply that with 1000. So this is what we require. First of all, we'll require the number of moles of K2CO3. How can we calculate that? Number of moles of K2CO3. What is the number of moles of K2CO3 going to be calculated as? It's going to be given mass. What is the given mass of K2CO3? It's it is 20.7 grams. So we're going to have 20.7 divided by what? By the molecular mass of potassium carbonate. What's going to be the molecular mass of potassium carbonate? It's going to be 138 grams per mole, right? This is also in grams. You know how to calculate that, right? So just add up everything in K2CO3, will come up to 138. So that will make you what? That will give you the number of moles of K2CO3. That's going to be 0.15 moles. If you calculate this, if you divide this, you'll actually get an answer of 0.15 0.15 moles. Now there is one more thing we require the mass of solvent. Obviously it's going to be water in this particular case, because potassium carbonate is dissolved into water to make a solution. Then mass of solvent. Now this is an interesting thing. How do we calculate that? We have the mass of solution. What is the mass of solution? Mass of solution is 500. But how do we make mass of solution? Mass of solution is made up of what? Mass of potassium carbonate plus mass of solvent, which is going to be water. Then how do we calculate the mass of solvent? The mass of solvent will be mass of solution minus mass of K2CO3, which is going to be 500 minus of 20.7, which will actually give us a value of what? That will give you a value of 479.3 grams. So actually this is the mass of solvent. Now it's a pretty easy question. We just have to divide. What's going to be the molality? Molality will be number of moles divided by the mass of solvent in grams multiplied with 1000. This is how we'll actually calculate that thing. What will this particular thing come up to? This will come up to 0.313 moles per kg. We can actually write the answer as 0.313 moles per kg, and this will give you the molality of this particular potassium carbonate. Do we all understand that thing? First of all, find out what is the mass of the solvent, find out the number of moles of solute, and just divide it. You have to get the molality of that particular solvent. Do we all understand this thing? It's a pretty simple concept, guys. Any problem, rewind the video, pause the video, go back to the video and watch it all over again, just to make sure that you understand and get the concepts really clear. We all are good with this thing? Great. Let's move on to the next unit of concentration, a mole fraction. This is a pretty easy one. What is a mole? It's a fraction, right? But what's the fraction of? It is a fraction of a mole. Then what is it? It is the ratio of the number of moles of one component to the total number of moles, which is solute and solvent combined present in the solution. So what is it? It is a ratio. Remember, mole fraction is always represented by x. Either it can be uppercase x or lowercase x. So it depends upon how you are representing it. Both are going to represent the same value, right? So mole fraction will be the number of moles of any one component with respect to the total number of moles of the entire component or the entire solution, right? Let's say there are two components in a solution, A and B. Then if you have to calculate XA, which is going to be the mole fraction of A, how will we calculate this? We'll calculate this by dividing the number of moles of A. This is number of moles of one component, right? So number of moles of A with respect to what? The total number of moles of solute and solvent, rather solution. So it has to be Na plus of Nb, the number of moles of A with respect to the total number of moles present in the solution. Similarly, if we have to find out the mole fraction of the second component B, how do we calculate? The number of moles of B with respect to what? The total number of moles present in the solution. Na upon Na plus Nb or Nb upon Na plus Nb. Now tell me quickly, what is going to be the SI unit? What is going to be the SI unit of mole fraction? It will have no unit. Why would it not have any unit? Because we are dividing the number of moles with respect to the total number of moles. That means both gets cancelled out. Thus, mole fraction does not have any unit. Remember this point, right? It's an important point again. Now if I ask you, what if I do this? If I find out XA plus XB, what is meant by XA plus XB? We are trying to add the mole fractions of both the components. Then XA plus XB will be equal to what? Na upon Na plus Nb. And we'll add this into what? It will add this into Nb upon Na plus Nb. It's a pretty simple math, right? And we pretty much know that it will come out to what? Na upon Na plus Nb upon Na plus Nb, which is going to be equal to 1. Why 1? Remember probability. Probability is that all the events, when we add everything, then the total probability comes out to be 1, because that's the maximum value for an event, right? Similarly, the maximum value for the entire solution should be equal to what? 100%, not more than that, right? Similarly, that means if I have XA plus XB, then that will always be equal to 1. What does this tell me? That means if we are given the mole fraction of any one component, we can calculate the mole fraction of the other component by subtracting the first by 1. That means if you have to find out XA, we can write it as 1 minus of XB. We can do this thing. Otherwise also we can also write XB equal to 1 minus of XA. So these are the two things that we need to understand very clearly. Do we all understand this thing? But this is only for two components. What if we have n components in a given solution? We have more than one component, for example. So let's say we have first component as A1, then the second component as A2 and A3, and so on, for example, up to AN. There are N components present in a particular solution. Then how will you calculate the mole fraction of all these components? What will be the mole fraction of the first component? It's going to be N1 upon N1 plus N2 plus N3 up to what? N, for example, right? That is how we are going to calculate that particular part. Let us say there are N particles this way, right? So we can also write it in general form. Let's say there are I particles, then it can be written as Ni, the number of moles of the ith particle. Similarly, what's going to be the mole fraction of the second particle? It's going to be what? N2 upon N1 plus N2 up to Ni. Then similarly, what's going to be the mole fraction of the ith particle? The mole fraction of the ith particle will be Ni, number of moles of the ith particle with respect to the total number of moles, that is N1 plus N2 up to Ni. Now, can we write all these things into a summation form just for the sake of simplification? Yes, we can. What's going to be xi? X1 will be equal to what? N1 upon summation of Ni, where I goes from 1 to n. We can write it this way, right? Because Ni summation will actually represent N1 plus N2 up to Ni, for example, right? Or Nn if there are N particles in that case. Similarly, what's going to be x2? X2 can be written as what? N2 upon summation of Ni with respect where I goes from 1 to n. We can actually write it this particular way, right? Similarly, what's going to be the mole fraction for xi represented as? It can be represented as number of moles of ith particle with respect to the total number of moles present in that solution for n particles or I particles. It can go up to any of that particular term. We all understand this thing. This is how we calculate the mole fraction if we have more than 2 components or we have I or n components in a given solution. Are we all understanding this thing? Great. Let's move on to the next unit of concentration. Probably this is our last unit of concentration, normality. Now we have come across this term quite often in our laboratories as well. We are doing some experiments and we are given a solution. Either it's a m by 10 or a m by 20 solution, or it can be an n by 5, n by 10 solution. So what are those solutions? Those are molar solutions or normal solutions. So right now we are dealing with normality. So what is normality of a solution? It is the number of gram equivalents of a solute. Now this is very important. This is the number of gram equivalents of solute dissolved per liter of the solution. Again, it is dealing with what? It is dealing with volume of the solution. How is it represented? It is represented by capital N, uppercase N. Again, remember or understand the definition. It is the number of gram equivalents of the solution, solute with respect to volume of solution in liters. What is the formula? The formula is the number of gram equivalents of solute with respect to volume of solution in liters. Right? Now, how do we calculate gram equivalents? Gram equivalent of solute. How do we calculate gram equivalent of solute? We can calculate this by finding out mass of solute, absolute mass, right? Not molecular mass. Mass of solute, or in case in the formula that has been given in our video right now, it's the weight. We can write mass of solute or weight of solute. Mass of solute with respect to the equivalent mass. With respect to equivalent mass or weight. Equivalent mass or weight of the solute. Either that you can write, right? Now, first of all, we had a term of gram equivalent. Now we have a term of equivalent mass or equivalent weight. Now, how do we find out equivalent mass? Then equivalent mass can be found out by, we can divide the molecular mass of the solute with respect to its acidity or basicity. Now, what is acidity or what is basicity? What is acidity? It is the number of hydroxyl ions that a base will liberate in a solution. It's absolutely opposite. Acidity is calculated for a base. Basicity is calculated for an acid. What is basicity? It is the number of H plus ions that an acid can produce in a solution, right? So these are the things that we'll need to find out the normality. First of all, I always go opposite. First of all, I always find out equivalent mass. Then I put it here to find out the gram equivalent mass. Then I put it in this particular formula to find out the normality of the solution. Right? So this is what normality is all about. It's the number of gram equivalents of the solute with respect to the volume of solution in liters. If it is not in liters, if it is in ml, multiply that formula with 1000 so that the entire thing gets converted into liters. How is it represented? It is represented by capital N. What do we all require to find out the normality? Well, first of all, require the gram equivalents. Gram equivalents are calculated by what? By dividing mass of solute with respect to equivalent mass. And how do we calculate equivalent mass? By dividing molecular mass with acidity or basicity. Do we all understand that particular part? It's a pretty simple thing. It's not a difficult thing at all, right? Now what's going to be the SI unit of this thing? What's going to be the SI unit of normality? You guessed that right. It's going to be gram equivalents per liter. Gram equivalents per liter. That is what's going to be the SI unit of normality. Now again, normality is depending upon what? What does the normality formula have? Normality is depending upon what? It's depending upon volume of solution. And if it is depending upon the volume of solution, what would happen? It will change with temperature. So this will change with temperature against what? Because as the temperature changes, then there will be expansion or contraction of liquid that will change the normality of the solution. Then if someone is asking you what is the best unit of concentration amongst molality and normality on the basis of temperature, then molality is the best thing because it will not change with temperature, whereas normality changes with temperature, just like molarity was changing with temperature as well. Do we all understand this thing? Great. Let's move on to the next thing. What do we have now? We have a question again, as we have been doing now. We were doing a concentration unit and we are putting up a question on that just to make sure that we are good with the calculation part of this particular part. Now what is the question? The question says that we have to calculate the normality of a solution containing 31.5 grams of hydrated oxalic acid. The formula is given. What is this dot 2H2O here? This is the water of crystallization. That is why it is in hydrated oxalic acid, right? Oxalic acid is what? H2C2O4. And this has been given into what? It has been given into 1250 ml of solution, 1250 ml of the solution. So we require the volume of solution in ml, so that is directly been given. But we also require a lot of things in here. I have told you I actually go opposite to what is required in the formula. First of all, I'll write the formula. How do we calculate normality? We'll calculate that by finding out the gram equivalents of the solute. That means of H2C2O4.2H2O. That's a solute. With respect to what? With respect to volume of solution. Volume of solution in ml. Right now it is given in ml, and that is why we have to multiply this with 1000. Now first of all we'll find out what gram equivalents. How do we calculate gram equivalents? Gram equivalents can be found out by dividing what? By dividing the mass of solute. What is solute in this case? The mass of solute, the solute is H2C2O4.2H2O. This is the solute in this case upon what? Divided by its equivalent mass. So this is the term that we have to find out first. Now what is equivalent mass? We'll have to find out equivalent mass so that we can find out the gram equivalent mass. Now how do we calculate the equivalent mass? Equivalent mass is calculated as what? It is calculated as molecular mass. So molar mass of H2C2O4.2H2O divided by its acidity or basicity. I had told you this thing, right? Divided by its acidity or basicity. Now oxalic acid is an acid. That means what do we calculate? Acidity or basicity? We'll try and find out the basicity of this thing. Now what is basicity? That how many H plus ions can oxalic acid give in a solution? How many H plus ions can it give? It can actually give 2 H plus, and we have a stoichiometric formula here. Then the formula has made it as H2. H2 means what? That means there are 2 H plus ions available for this particular solution. That means I'll have to divide this with 2. What is the molecular mass of H2C2O4.2H2O? If you calculate the entire thing, that will come out to be 126. That is the molecular mass upon 2. That means what is the equivalent mass of the solute? The equivalent mass of solute is 63. Now what do we have to find out? We'll have to first of all find out the gram equivalent. What is gram equivalent equal to? It is the mass of the solute. What is the mass of solute given as? It is given as 31.5. We are already given that particular mass. And we'll divide that with what? We'll divide it with the volume of solution. But do we need to volume solution? No. We'll have to first of all divide it with equivalent mass so that we can find out the gram equivalent mass. What is the equivalent mass? Equivalent mass is 63. We just found that out. It will be divided with 63. Then what does this particular thing produce? This will actually produce an equivalent gram equivalent mass of what? 0.5. This will actually be the gram equivalent mass of hydrated oxalic acid. Now we'll find out what? We'll find out the normality of that solution. Normality will be equal to what? Normality will be gram equivalent of hydrated oxalic acid, which is going to be 0.5. This will be divided with what? Volume of solution in ml, which is going to be 1250, and that will be multiplied with what? It will be multiplied with 1000. so as to convert that into liters. Then if we solve this entire thing, what's going to be the answer? The answer is going to be 0.4 gram equivalents per liter, which is the SI unit of normality, or we can also write it as 0.4 normal only, right? So either of that thing is going to be correct, but the answer is going to be 0.4 normal or 0.4 gram equivalents per liter. Do we understand that thing? First of all, what did we find out? We found out, I mean, this is what I usually do. I find out the equivalent mass first, then I find out the gram equivalent mass, and then I find out the normality. So this is how we can actually proceed to find out the normality of a solution. Disadvantage of normality, it will change with temperature due to expansion or contraction of the solution. Do we all understand this thing? This is a pretty interesting and a pretty simple thing. It is not at all difficult, right? Now what do we have next? We have some key points. Now these are very important key points to use them in your competitive exams or to find out the MCQs really quickly, right? So we can understand these key points. First of all, what is that relationship between normality and molarity? So if there is a question which deals with normality and molarity both, then what is the relation between this? Normality is always equal to molarity into molar mass divided by the equivalent mass of the solute. Now how is this formula relevant? Let's try and find out and crack this formula. What is molarity equal to? What is molarity? Molarity is the number of moles. So let's say N divided by what? The volume of solution in liters. So volume of solution in liters. And as per this formula, molarity is getting multiplied with what? With molar mass. It is getting multiplied with molar mass and is getting divided with equivalent mass. And it is divided with equivalent mass. Now let's try and crack this formula. What is number of moles equal to? Number of moles is equal to what? Given mass upon molecular mass. So given mass is W upon molecular mass, for example, is M into 1 upon V. This is volume, and into what? Molecular mass upon equivalent mass. And this cancels off. Then what are we left with? We are left with given mass upon equivalent mass and also divided by volume in liters. Now what is given mass upon equivalent mass equal to? If you remember the formula for normality, what was that particular part? If you calculate this particular part, that will actually come out to be the normality of that solution, right? So if you calculate it this way, you will understand the logic as well. Even if you do not understand it, you can also remember the formula, but if you understand that how to make that formula, this will be much easier for you guys, right? So normality is always equal to what? Molarity into molecular mass upon equivalent mass. This is the basic relation that we can always remember for our MCQs as well. Okay, what is the next thing that we have? For acids, what is normality equal to? Normality is equal to molarity into basicity. That means in this formula, what is this thing representing? This thing is actually representing either it is acidity for bases or basicity for acids. So this is what is this particular thing actually representing to us right now. Okay, so for acids, normality will always be equal to molarity into basicity, where basicity is what? It is the number of H plus ions that a molecule of an acid can give in a solution. For example, we have a question here. What is the basicity of H3PO4? How many hydrogen ions can H3PO4 release? How many ions do we see here? There are 3. Then basicity of H3PO4 will be 3. Similarly, for bases, what will be normality? Normality will be molarity into acidity, because for bases we calculate acidity, which is what? The number of OH minus ions that a molecule can give in a solution. Then in this particular question, how many OH minus ions can we see actually? We only have one OH minus. So in that case, what is the acidity of potassium hydroxide, KOH? It's going to be 1. Do we understand this particular key point? The normality and the molarity relation, that normality is always equal to what? Molarity into molecular mass upon equivalent mass. Acids, molarity is going to be normality will be molarity into basicity, and for bases normality will be molarity into acidity. Do we all understand this particular point? Great. So these were the important key points that you need to keep in mind to actually solve a particular numerical or a question. Okay, all good with this thing? Great. Let's move on to the next key point then. What is the next key point? That if V1 ml of a solution of molarity M1 is mixed with V2 ml of a solution of molarity M2, then the molarity of the final solution M3 will be what? It will be M1 V1 plus M2 V2 is equal to what? M3 into V1 plus V2. So if you are given two solutions, with different molarities, with different volumes, and if they are getting mixed to form a common solution, we pretty much know that if there are two solutions and if one has a volume of 5 ml and the second has a volume of 10 ml, then when we add both of them, we'll actually get the total volume as 15 ml, because the volume will always add up. So that is why we are seeing that the volume does not change. The volume still remains as V1 plus V2, but the molarity changes, right? So M1 V1 plus M2 V2 will always be represented as M3 into V1 plus V2, and from here we can calculate the molarity of that particular new solution. Similarly, what is the next key point do we have? That to dilute V1 ml of a solution of molarity M1 to molarity M2, so that the final volume is V2, then the volume of water to be added, that is V2 minus V1, will be equal to what? It will be equal to M1 minus M2 upon M2 multiplied with V1. So for example, if you are given a solution of certain molarity M1 and now the question says that you have to add certain amount of water, let's say certain amount of water has to be added so that the final volume becomes V2. Obviously the volume will change, right? So volume becomes V2, but the molarity will also change to M2. Then what is that amount of water added, right? Then the amount of water added will be equal to V2 minus V1, and that will be calculated as what? It will be calculated as M1 minus M2 upon M2 into V1. Now we pretty much have this relation. How can we calculate this particular relation of V2? How can we get that thing? We can actually find it by using this formula where M1 V1 should be equal to M2 V2. But M1 V1 is what? The undiluted level when the water was not added. So here it is undiluted when water is not added. Water is not added, it's undiluted. But now when we add water, then the molarity changes and the volume changes. And this is going to be when water is added. When water is added, so it becomes a diluted solution now, obviously because we are adding water to that thing. So from here we can calculate V2. What's going to be V2? V2 will be M1 V1 upon M2, and we can put this value of V2 in this particular relation. Now we can put it here now to find out the difference of V2 minus V1. We understand this particular logic. So these are the key points that we need to remember, guys. The relation between normality and molarity, and also these relations regarding molarities, because these are very important in context of the numericals that we face in our board exams and also in JEE Mains and Advanced both, guys. Okay. Now what do we have? We have some solved problems. So the first solved problem, again pause the video first of all, try these questions yourself and then come back to my solution. Okay. So what is the first solved problem? The mole fraction of benzene in a solution with toluene is 0.50. What is benzene? Benzene is C6H6. We all know that thing, right? What is toluene? We all know what is toluene, right? Toluene is C6H5CH3. We all know what is toluene, right? So in that, which is methyl benzene, commonly known as methyl benzene, or it has an IUPAC name of methyl benzene as well. So in that case, mole fraction of benzene in a solution with toluene is given as 0.50. We have to calculate the mass percentage of benzene. Now remember, this question is regarding a very early topic that we discussed in this unit. Mass percentage. We have to calculate the mass percentage. Mass percentage is what? Weight of a given component with respect to the weight of the solution, and that is multiplied with 100. We already know that particular part, right? So first of all, we'll have to find out the mass of the individual components. That is how we'll actually proceed with this question. So let us say we do not know that what is the total mass, right? We do not know that thing. So let's say if we have a total mass of 100 grams for the solution, if the solution weighs 100 grams, and if I say that it has X grams of benzene, then what will be the mass of, or let's say it does not have X grams of benzene, but it has the X mass percentage, the X percent of benzene, for example, right? X percent of benzene, for example. Then what's going to be the mass percentage of toluene in this case? The mass percentage of toluene is going to be 100 minus X, 100 minus X percent. That will give you the mass percentage of toluene, which is C6H5CH3. C6H5CH3. We all know that particular part, right? Now, how do we calculate the number of moles first of all? What is the number of moles right now, right? So in that case, if X percent of 100 grams is going to be what? X only. So we can have X grams of benzene here, and what's going to be 100 minus X percent of, out of 100 grams of the solution, it's going to be 100 minus X grams of toluene as well. So we get the mass of the individual components first of all. We have got the mass of the individual components. Now let's calculate the number of moles of benzene first of all. Why? Because we are given the mole fraction. So we'll have to get into mole fraction somehow. So we'll calculate the number of moles first of all. So number of moles of benzene, which is C6H6, which is given by what? Given mass upon molecular mass. What is the given mass? We do not know the given mass, but we have assumed it to be X grams. So given mass upon molecular mass. What is the molecular mass of benzene? It is 78. Similarly, what is the number of moles of toluene? Number of moles of toluene, which is C6H5CH3. How do we calculate the number of moles of toluene? It's going to be number of given mass, which is going to be 100 minus X upon what? Its molecular mass. What is the molecular mass of toluene? Calculate. It's going to be 92, right? When we calculate, we'll get the molecular mass as 92. Now what do we have to find? We have to find out the mole fraction, because mole fraction is already given as 0.50, so we can equate it with this, right? So how do we calculate mole fraction? The mole fraction of benzene. So X of C6H6 will be equal to what? Number of moles of benzene, which is X upon 78 upon what? Total number of moles, which is X upon 78 plus of 100 minus X upon 92, right? And this should give you the mole fraction, which is actually equal to what? 0.50. This will give you the what? The mole fraction of benzene. But this gives you a very simple linear equation now, right? When we entirely solve this, we'll get the value of what? We'll get the value of X. What does the value of X come out to be? Calculate quickly, guys. The value of X comes out to be 45.9. The value of X is coming out to be 45.9. But what was X actually equal to? It was, I have assumed it as the mass percentage of benzene, which was supposed to be found out, right? Therefore, the mass percentage of what? Of benzene. The mass percentage of benzene comes out to be 45.9% in this particular solution. If someone is going to ask you that what is the mass percentage of toluene as well, how do we calculate that? We can actually just subtract 45.9 from what? From 100, because that is the total percentage, and that is how we'll get the mass percentage of toluene as well. Do we all understand that thing? The question was asking us the mass percentage in context with the mole fraction of the solution. So very important question again. What do we have next now? We have another salt example for you. What is the salt example for? This is mole fraction of water in sulfuric acid solution. So we are given sulfuric acid solution now. So the mole fraction of water in sulfuric acid solution is given as what? It is given as 0.85. We have to calculate what? Molality of the solution. Interesting question again. We have to calculate the molality of the solution. How do we calculate the molality of the solution? Molality is given by what? The number of moles of solute with respect to what? With respect to mass of solvent in kg. If it is not in kg, we can actually convert that into kg by multiplying with 1000. If the solute is given in grams, we can pretty much know that particular part, right? So there are two methods to this thing. I'll do the easier method. You can also do it with the basic method if you want, right? But I'll do it with the easy method. What are we given? We are given the mole fraction of water now. We are given the mole fraction of water, and in sulfuric acid solution, that means the solution has sulfuric acid and water both. Then how do we calculate the mole fraction of water? So X for water will be equal to what? Number of moles of water upon what? Number of moles of water plus number of moles of sulfuric acid will be, that is how we'll get the mole fraction of water. That is already given as 0.85. So 0.85 should be equal to what? Number of moles of this particular part, right? Let's find out the number of moles of sulfuric acid as well, and then we'll try and find out the relation. So H2SO4, that will be equal to what? That will be equal to number of moles of sulfuric acid with respect to what? Number of moles of water plus number of moles of sulfuric acid. Do we all understand this thing? I have just put up the formula for number of moles to find out the number of moles of, mole fraction of water and mole fraction of sulfuric acid. Now this is already given as what? This is already given as 0.85. Then tell me quickly, what should be the value of the mole fraction of sulfuric acid? It is a binary solution, right? There are just two components, water and sulfuric acid. Then if the mole fraction of water is 0.85, then the mole fraction of sulfuric acid should be equal to what? Should be 1 minus of 0.85. I have already told you this thing. It's always 1 minus of the component's mole fraction, right? So that should come out to be 0.15. Now if I just mark these as two equations, and if I just do this thing, I do 1 upon 2. What is meant by 1 upon 2? 1 upon 2 means mole fraction of water upon mole fraction of sulfuric acid. That should be equal to what? That should be equal to 0.85 upon 0.15. But formula wise, it should be equal to what? It should be equal to number of moles of water with respect to number of moles of sulfuric acid, because the denominator are the same. They will actually cancel out. Do we all understand that thing? So now what do we can calculate from here now? We can actually get a relation. We can actually get a relation for what? We can get a relation for to find out the molality of sulfuric acid, of the solution rather, because it is in context with the solute in that particular case. So now what do we require? We'll require the number of moles of water first of all, right? The number of moles of water. How do we calculate the number of moles of water? Tell me quickly. Number of moles of water will be equal to what? Given mass upon molecular mass. Now we are given that particular molality. Molality is always in terms of what? It is always in terms of 1 kg of water as a solvent. 1 kg of water will have a weight of what? 1000 grams, right? So given mass will be 1000 grams upon its molecular mass, which is 18 grams. How many number of moles of water come out to be? It always comes out to be 50.55. Make sure you remember this value, guys. It's an important value, that 1 liter of water, I had told you earlier, 1 liter of water will always be equal to approximately 1 kg. Then 1 liter of water will always have the number of moles as 55.55, or 1 kg of water will always have 55.55 moles of water. Do we all understand this thing? What am I supposed to do now? Just put the value of number of moles here now to find out the number of moles of sulfuric acid. That means 0.85 upon 0.15 should be equal to what? 55.55 upon number of moles of sulfuric acid, right? This is how we're going to find out. So we can calculate the number of moles of sulfuric acid from here. What's going to be the number of moles of sulfuric acid when you calculate this entire thing? The number of moles of sulfuric acid will come out to be 9.8. This is what is going to be the final answer, right? Number of moles of sulfuric acid is 9.8. But this is what we are supposed to find out. We are supposed to find out what? Molality. Then molality is what? Number of moles of sulfuric acid with respect to mass of water, but it has to be in kg, right? And we had already assumed this to be in kg, which was how much? It was equal to 1 kg. That means the molality will actually be equal to what? The number of moles itself. That means the molality comes out to be 9.8 molar solution. So this is how we actually calculate the molality of that particular solution, by actually equating that with 1 kg of water, and thus whatever the number of moles of sulfuric acid come out to be, they are actually the molality of the solution as well. If you wanted, you could have actually done that with respect to the basic formula as well. That was still the same thing. Do we all understand that thing? It's a pretty simple problem. If you have a problem, just go back a bit and find out the entire solution again and understand the entire logic again. Okay, great. Do we all understand? These were the 2 solved examples that we have. Now what do we have? The big deal. The big deal as the homework assignment for you guys. How many questions do we have for homework now? Just 3 problems. Pretty simple for L1. L1 is lecture 1. So the first problem is 1 liter of N/2 HCl is heated in a beaker. It was observed that this is basically it. Okay, so it was observed that when the volume of the solution is reduced to what? 600 ml, 3.25 grams of HCl is lost. You have to calculate the normality of the new solution. Second question, 100 ml of a solution containing 5 grams of sodium hydroxide are mixed with 200 ml of M/5 sodium hydroxide solution. You have to calculate the molarity of the resulting solution. Remember the key points? The question is completely based on that. Then the third question, the molarity of a liquid hydrochloric acid if density of the solution is 1.17 grams per centimeter cube is what? There the 4 options are given. You have to find out the molarity if the density is that much. Are we all clear with these 3 problems? So again, make sure you're done with these 3 problems. By the next class, you will have the solution for these problems in a separate video. We'll create a separate video for that thing to discuss all these 3 problems. We can also discuss them during your live classes as well. So that's it from me for this particular lecture, guys. I'll see you guys in the next video, lecture 2 for solutions. We'll discuss the next topics of solutions. Till then, bye bye and have a great day ahead, guys. Take care.